Okay, good afternoon, lads and ladies. Welcome back to Calc 2. Today we are going to talk more about integration by parts as we begin our headlong plunge into integration methods. Let me fire up the doc cam, start sharing my screen, and we can get into it. Oh. So this is MAC2312. You guys are section 004. It's a lecture. Well, we will have a lab later, 2121. Today, sorry, 1 second. Oh, okay. Someone was poking around at my car in the parking lot. All right, so today we're going to talk more about IBP. More integration by parts. This is our second lecture on IBP, and this is section 7.1 in the textbook. That's all I have planned for today, right? We're just going to do more IBP. Believe me, that's plenty. So, in service to that, there's a couple kind of categories of integration by parts problems. I'll remind you real quick, last time we saw how to integrate what do we do? We talked about like polynomials, times something like e to the x or cos x or sine x, right? All of these, if you're going to integrate something like this, dx, all of these are IBP. And you'll always run this with u as the polynomial piece and dv as whatever else you have over here. We also saw, so this is kind of the first family of things that we saw, inverse functions. So like natural log of x or inverse trig. Stuff like that, functions that are defined as the inverse of some other function. Today, I want to show you how to handle a few special cases. So today, we're going to look at some harder IBP. One of these is something like e to the ax times sine of bx or cos of bx, these sort of things, which you'll hear me refer to as damped harmonic oscillators. The other things we'll be looking at here are integrals of odd powers of secant. And like I said, this one up here is called the damped harmonic oscillator. Okay, so these are the two kind of families of integrals I'm going to invest most of the time in today, and you'll see that those are plenty for us to practice with. I also want to spend some time working on just definite integrals by parts. We did one of these the other day. I would like to do at least one more definite integral by parts, just to give you a more comfortable or better feel for how they differ from indefinite integrals done by parts. Now, my wife just came home, so I'll ask you to hold on for 1 second while I close the door. All right. So let's begin with the third item down here. I think this is actually the easiest thing, and we can connect it most readily back to what we were doing, and then I'll move to these other two. So let's look at a few definite biparts problems. One of these I like a lot. I'd like to show you really quickly here as a fun problem. Let's evaluate the integral from -1 to 1 of the inverse tangent function. So this is a function defined as the inverse of another function. In our Lipet hierarchy, it's the second tier. So we know what we're going to do. We're going to run IBP with u equal to the inverse tangent of x. And dv as everything else, which in this case is just dx. If u is the inverse tangent of x, then du is the derivative of the inverse tangent of x, which is 1 over 1 plus x squared dx. And v would be the integral of dx, which is just x. So this is us filling out our IBP table. Any questions about how we filled out that table, where those pieces came from? All right then. So what we do now is we just follow our formula. The integral of u times dv is equal to u times v. So that's the inverse tangent of x times x. But since this is a definite integral, this piece needs to be evaluated between bounds minus the integral, again, between the same bounds of v times du. And one of the last problems we did on Tuesday was the integral of the inverse sine function, right? And I said all of the inverse trig integrals go the same sort of way. You run IBP, and then in the integral you get out from IBP, you need to do a substitution. I'll also go ahead and do this evaluation here. It's a good habit to do that right away. So this is going to be the inverse tangent of 1 times 1 minus the inverse tangent of -1. I'll write that like that for now. And then over here, I'll write this as this is just integral -1 to 1 x over 1 plus x squared dx. And now I need your guys' help for a few things. Let's start on the far left. What is the inverse tangent of 1? What is this?
It's arctan, correct?
Yeah, same as arctan of 1. What is arctan of 1?
It's 1, right?
No, not 1. So remember the definition of the inverse trig function. This is very important. The inverse tangent of x is equal to y means that x is equal to the tangent of y, and y is between -pi/2 and pi/2. Right? This is the definition of the inverse tangent function. So the inverse tangent of 1 is the angle such that the tangent of that angle is equal to 1, and that angle is between -pi/2 and pi/2. So what angle between -pi/2 and pi/2 has tangent 1?
Pi/4.
Good, right? Very good. So I'll rewrite this in the specifics here, right? The inverse tangent of 1 equals y means that 1 is equal to the tangent of y, and negative pi over 2 is less than y is less than pi over 2. I don't mean to belittle anybody or make anybody feel bad, but if this is not immediate, then you need to spend time. Where is it? Here. Oh, this is an old class, sorry. Same shit. You need to spend time back here in the trig review. You got to spend that time and make sure you really understand the inverse trig functions, or it's going to bite you in the ass. It's going to bite you in the ass again and again and again in this class. So knock it out now, right? Come back here to the algebra trig review from Paul's online notes. You can go to the trig specific review here and look at the inverse trig stuff. Make sure you know your unit circle. Make sure you know the definitions of these inverse trig functions. Make sure you know and understand what the domain restrictions are, why we talk about this. All right. So the inverse tangent of 1 is pi over 4, because the tangent of pi over 4 is 1, and pi over 4 is between negative pi over 2 and pi over 2. What about the inverse tangent of negative 1? So what angle between negative pi over 2 and pi over 2 has tangent of that angle equal to negative 1?
Negative pi over 4?
Beautiful, negative pi over 4, right? I'm going to draw the picture here because this is one where the domain restriction is something usually we really have to think about a little bit carefully. Here is, there's actually 2 points on the unit circle where the tangent function is equal to negative 1. Right down here, which is root 2 over 2 comma negative root 2 over 2. And over here, which is negative root 2 over 2 comma positive root 2 over 2. This guy is the guy we're going to need, and we're going to think about him as rotating down negative pi over 4 to get there. This guy is no good because we have to go past pi over 2. And right, pi over 2 is the north pole here. So if you have to go past pi over 2, that's no good. And for that same reason, I cannot think about this other guy like that, because then I would be walking way past pi over 2. So we need to be between negative pi over 2, which is rotating backwards down to this point, and positive pi over 2, which is rotating forwards up to this point. We got to be between those for the inverse tangent function. So negative pi over 4 is perfect. Okay, how do I do this integral? I'll swap these in our next line. How do I do this integral?
Substitute 1 plus x squared.
Very good. And I'm going to use a letter different than u because we've used the letter u up here to mean something already, and I don't want to confuse the variables. So I'll use the letter z for my new variable here. I'll let z be 1 plus x squared. Then dz, the derivative of 1 plus x squared, is just 2x. So dz is 2x dx. So there's the substitution we're going to use. Because this is a definite integral, I also need to change my bounds, and something funny is going to happen here. So I'll write my old bounds. My old bounds are x equals negative 1 and x equals 1. When x is negative 1, z is going to be 1 plus negative 1 squared. Well, that's 2. And when x is positive 1, z is going to be 1 plus positive 1 squared, which is also 2. So here's what we end up with. I've got pi over 4 minus negative, minus negative pi over 4. Oh, there's a negative 1 here, sorry. We also need a negative 1 here, just like there's a positive 1 here. So this times negative 1 from the x. There we go. Minus the integral from 2 to 2 of the x1 plus x squared downstairs, that's just z, and then x dx, that's 1/2 dz. So I'll have a 1 up here, and then 1/2 dz like this. So up front, I've got pi over 4 minus 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 pi over 4. That's 0 minus 1/2 integral from 2 to 2 of 1 over z dz. What is the integral from 2 to 2 of any function? Forget the fact that it's 1 over z inside there. Just based on this piece, can you tell me what this integral's value is?
0.
Very good. Integral from a to a is always 0. So this piece is 0 by virtue of bounds. All right, so my whole result here is 0 minus 1/2 times 0, which is 0. So this integral is 0. And it's a kind of funny example. We do our integration by parts. That gets us here. Up to here, it's a pretty normal IBP problem. But then as you move down, some funny things happen. When we evaluate this piece, right, when we evaluate between bounds here, this piece, inverse tangent of 1 is pi over 4. And then we have to subtract off what we get when we plug in -1, which is the inverse tangent of -1 times -1. If you didn't get this -1 right here in your notes, go back and add it. I didn't write it at first. I messed up. I forgot about this x when I first wrote this down. So it needs to be a times -1 there. That gives me pi over 4 minus negative pi over 4 times -1, which is pi over 4 minus pi over 4, which is 0. And then this piece, when we make the very reasonable substitution, z equals 1 plus x squared, becomes the integral from 2 to 2 of 1 over z times 1/2 dz, which is 0, not because of something to do with the antiderivative, but because of the bounds. Sorry, they're cutting the grass outside my apartment. Now, one of the reasons I like this problem so much is because it can be done even faster. We applied a kind of symmetry trick at the end there. Does anybody see a symmetry trick that could be applied at the start? This problem can be done in a single line.
Graph it like the same areas above the curve as below, so.
Yeah. What kind of function is the inverse tangent function? So I think I drew this graph for you once before. But if it's not in the brains nice and solid already, let's get it in there now. I've put this problem on exam 1 a few times, and the people who recognize that this function has a certain symmetry solve it very quickly. And people who don't recognize that tend to struggle quite a bit. Not that it's a hard problem, not that the IBP is especially challenging, but Arctan is an odd function. The area bounded on the right above the x-axis is equivalent to the area bounded on the left below the x-axis. So because f of x equals inverse tangent of x is an odd function, continuous on the interval -1, 1, it follows that the integral from -1 to 1 of the inverse tangent of x dx is 0. And that's true for any odd function. You integrate any odd function over a region or interval symmetric about 0, you'll always get 0 because these areas always cancel out perfectly. So this is the graph of arctan. We should all know it. And we should be comfortable with the definition of the inverse tangent that we had up in blue a minute ago and we needed to evaluate. I could change this to the integral from 0 to 1, and then you can't use that symmetry argument anymore. You would actually need to evaluate the integral. So please take to heart the actual steps in the solution there, because those are important. But this is a good example of a problem that has another faster solution if you think about it a little bit more deeply. Draw the graph. So it's one of those reasons we say when you're working an area problem, you should always draw the picture, right? Simplifying symmetries show up all the time and can really be useful. All right. Questions on the solution here? The actual steps, the integration by parts?
Actually, I do have a question.
Yeah.
Like on the test, say we like find symmetry. Do you still want us to like write down all the work so we get credit, or can we just graph and we'll get like full credit?
Now, if so, on exam 1, if I gave you this problem, you draw me this picture, you write this sentence, and the answer here, and you're Gucci. That is a perfectly valid solution.
All right, thank you.
Any questions about the actual steps here, though? Because I could give you this as an indefinite integral. I could give it to you as the integral from 0 to 1. And in any of those situations, you still need to do this computation. Are there any questions about how we do the IDP here? Okay, then. All right. We'll move on.
Professor,
Oh,
one question.
sure, Ariel, yeah.
So when you get to the part where you have 1/2 dz, I don't see how you got the 1/2.
Maybe it would be worthwhile to run this as an indefinite integral. Let's see if I can answer the question quickly. So here, 1/2 dz would be equal to x dx, right?
Correct.
So here is my x dx, and I replace that by this 1/2 dz. And then the remaining piece, the 1 over 1 plus x squared, that becomes this 1 over z. Does that clear that up?
Yes, much clearer. Thank you.
Okay, cool. All right, then I won't go through this as an indefinite integral. I'll leave that for something you guys can do on your own if you want to. It occurred to me, I've been getting some emails about the homework, and I wanted to make clear. First, always happy to receive emails about homework. It makes me happy to know you guys are working problems outside of class. It's a good thing. Don't ever hesitate to email me. But the homework is meant to be like the bare minimum. I give you on WebAssign what I think is the absolute minimum to develop the skills requisite for this class. If you really want to develop your skills, you need to be solving many, many more problems. The textbook is your friend. So I fully encourage you guys, especially if you're interested in mathematics or engineering, science, anything like that, to get into the textbook and grind all the problems. I can't tell everybody you must grind all the problems. So the WebAssign homework is just the bare minimum. Keep that in mind. Okay, those two other challenging families of integrals, right? Looping integrals, we call them. And my favorite example of this is what's called the damped harmonic oscillator. There's a lot of things in nature that give us damped harmonic oscillators. Alpine, I recognize that it can feel like a massive time sink, and your comment there, I take it to heart, right? That's why I don't assign anymore. But it's true. Oh, what's a good analogy? I don't know if you guys have tried to skateboard, right? Try to learn how to do a kickflip or something. It takes hundreds of hours. We're talking tens of hours to get to a place where you can scoot your ass around on the skateboard without falling off. Tens of hours to do an ollie, and then tens of hours more to learn how to kickflip. Same sort of shit, right? You guys are at the learning how to kickflip phase in your mathematics right now. It's tens and tens of hours, and it needs to be done frequently. If you take long breaks in between, it falls apart. This is really just how it goes. Anytime you want to learn a new skill in life, a real skill, a valuable fucking skill, it takes time. It takes massive amounts of time, way more than people pretend like when they talk about this shit. People love, after they get through these classes, to talk about them like they were easy or like there's some sort of traumatic experience that just kind of happened. It's a lie. The truth is you need to be actively and intensely participating for hours and hours and hours every week, tens of hours, really, realistically, if you want to get good at it. So don't feel bad. If it feels like overwhelming, that's how it should feel. And grinding on it harder and more, especially grinding on it independently without leaning on other people or other resources, is how you become that badass. So don't stress if it feels scary or overwhelming. Don't stress if you feel a little intimidated. Just know that you're going through something that everybody has to go through to develop challenging skills. Okay, damped harmonic oscillators. These show up in nature all the time, but the simplest way for me to describe it is in terms of a spring mass dashpot system. You guys ever tried to slam a door at a 7-Eleven or a doctor's office or somewhere? It has that like rectangular box above the door with the folding arm. It kind of goes and it won't let you close the door too fast. That's called a dashpot. And a spring mass dashpot system is what it sounds like. I have a little wall over here. Attached to that wall is a spring. On one end of that spring, I have a little cart with a mass, M, whatever, some mass. And then on the far end over here, I have a dashpot, which is like a little shock absorber. Whatever, it's like standing on something, I don't care. All right. The idea is this: you pull the mass back and then you let it go. If not for the dashpot, it would wobble back and forth as a harmonic oscillator. It would just bounce back and forth, and that's a sine or a cosine. With the dashpot, it will wobble back and forth, but the wobbles will get smaller. Right? So such a system when tension is put on the spring, and the mass is released, and allowed to move, wobbles back and forth. But the dashpot, the term is dampens the wobble. So if I plot the position with respect to time, we'll get a curve looking something like this. Here it is pulled out to its maximum displacement. I let it go and it'll wobble back, but the dash pot's like, I'm gonna like dampen you a little bit. So you're not gonna go as far out as you did that first time. And then the spring pulls it back. But the dash pot again is like, I'm not gonna let you go out as far as you did last time. And the spring pulls it back towards equilibrium. But then the dash part is like, I'm not gonna let you go out as far as you did last time. And it keeps doing this. And you get this decaying or damped oscillation, right? Where it oscillates less and less each cycle. The classic example of this, I'm going to use t as my variable because I'm thinking of it as time, is e to the minus t times the cosine of t. So this is my t-axis. I'll show you in Desmos, but that's the idea, right? So I pull this box way back over here and I let it go. The spring pulls it in, but the dash pot doesn't let it go so far, and then back and forth and back and forth. And each time the dash pot dampens the motion. The spring just wants to wobble. Let me show you in Desmos what I'm talking about. College algebra stuff. Sorry, my scales are set all sorts of weird. X-axis. Something like this. It's actually, this is too exaggerated. There's my vertical scale. Let me show you a simpler example here. I'll get a fresh graph so we don't have to mess with the scale so much. Right? So you see it starting to wobble, but very quickly that wobble gets dampened. A simpler example is something like 1 over x times cos x. This has weird behavior near 0. But again, you see it oscillating but dampening. Negative 1 to 1 is sufficient. So
Is this like the same thing as putting a capo on a guitar?
sort of. Putting a capo on it's like palm muting your guitar, actually.
Okay.
Right? So if you play guitar and you've done palm mutes where you like hold your right hand on the strings a little bit to dampen them so they don't wobble back and forth as fast for as long, it's like an open strum versus a palm mute. The decaying factor is this e to the negative x. That's usually what we see in nature is actually an exponential decay. It's just hard for me to get the scale set here so that you can see it well. I would like to, but the challenge is non-trivial because it decays so quickly. But it looks like this, right? With the appropriate scale settings, I don't want to spend the time fiddling there. It looks like this. So what we want to do, if I want to find out, for example, how much distance this mass covers wobbling back and forth before it stops moving, I would need to integrate this function. And this is what we want to do. We want to be able to integrate these. Now these show up in real life and in other less contrived ways. If you're looking above, imagine you have some high mass object like the sun or whatever, and you have some low mass object that's coming in to start orbiting. It's gonna spiral in eventually, right? Depending on the velocity it comes in with, if it doesn't come in with the appropriate velocity and at the appropriate angle, usually something like this will spiral in. If you look at this from the side, we see another damped harmonic oscillator, where your high mass object is here. Your low mass object, I'll draw it kind of like this, comes in and then comes around, but then it comes around less and comes around less, and eventually it's going to come in and collide. So this sort of back and forth wobble, but wobbling less each time, that is your damped harmonic oscillator. So your high mass and low mass objects. And in these instances, we might want to find out how long is it going to take before this thing that's spinning around our high mass object collides with the high mass object. If you had a satellite that was going to slowly spiral in and hit the Earth, you want to know when's that going to happen. All of these would require integrals of damped harmonic oscillators. So I hope that's enough motivation. The upshot is this. How do we compute, or we want to compute the integral of e to the x cos x dx. We'll start with this, and then I'll introduce like the negative and other numbers here, and then possibly other numbers here. And other things like it, right? I can't just integrate each piece on its own. I want to get that out there again. We talked about this before. This integral of e to the x cos x dx, this is very much not e to the x sine x. You can't just integrate each piece, because the integral of f of x times g of x dx is super duper not equal to the integral of f of x dx times the integral of g of x dx. This shit don't work. Just like it don't work for regular derivatives, it don't work for any derivatives, right? The regular derivative of a product is not the product of the derivatives, and the antiderivative of a product is not that. This is why we have integration by parts, because you can't do this. We need IVP.
That with constants, not with functions.
Even with constants, this rule doesn't work. You can pop out a constant, but the integral of a constant with respect to x would be that constant times x. So constant multiples pop out of integrals, but it still wouldn't satisfy this rule. It's an interesting note, but I don't want to burn class time there. But if, imagine f of x was a constant function k, then the integral of k times g of x is not the integral of k times the integral of g of x. It's just k times the integral of g of x. So even then, this doesn't work. Yep, result here is we need integration by parts, just like we need the product rule. So I want to walk you through the integral of e to the x cos x done by parts. It's a looping integral, and I'll show you why we call them looping integrals, but I want you to just kind of follow along with me, and we will see how it goes. So my aim is to integrate e to the x cos x dx, and I know it needs to be done by parts. If you follow your Lipet rule, there are no logs, there are no inverses, there are no polynomials, but there is an exponential. So I will pick u to be my exponential, which means dv needs to be everything else, which in this case is cos of x dx. Now we complete our IVP table. Du is the derivative of e to the x, which is e to the x times dx. And v would be the integral of cos x, who differentiates to cos x, that's sine of x. So here's my first little IVP table. And according to that IVP table, this integral here, integral e to the x cos x dx, is equal to e to the x times sine x minus the integral of sine x times e to the x, which I'll write as just e to the x sine x dx like this. Everybody with me so far? We know the derivative of e to the x is e to the x, so the differential of u equals e to the x is du equals e to the x dx. That's how differentials work. And if you integrate cos x dx, you get sine x. And then here, this is u times v minus the integral of v times du. I just wrote the e to the x out front because it looks prettier. It also kind of helps to inform us as to what we should do next. This integral is very similar to this integral. The only difference is the cosine turned into a sine. So if the mechanism we use to attack this is IBP, then the mechanism we use to attack this should also be IBP. All right. So I'm going to jump in with another integration by parts. Again, following LIPAT, I pick u to be e to the x and dv to be everything else, which this time is sine x dx. Du will be e to the x dx again, and v this time is negative cos x. So there's my second IBP table. Now, you need to be very careful with your negative signs. One person talked to me in office hours about how the negative signs are kind of what makes these problems hard, and that is 100% true. I'm about to replace this integral by an expanded thing, right? By a difference of two terms, which means I need to put the whole thing in parentheses because I'm supposed to be subtracting this integral, which means I need to subtract everything that I'm about to replace that integral by. So I need to open up a big paren here. And as long as you do that every time, you'll be okay. But you just need to be very, very careful. Anytime you're replacing a single term by a chunk of stuff containing multiple terms, you need to do so in parentheses. Now within here, we're going to have some negatives to deal with also. U times v, that's e to the x times negative cosine x minus, from my IBP formula here, minus the integral of v times du. Here's another negative, negative cos x times e to the x dx. Close that big paren. So look at all these negative symbols. If I was not super duper careful with all these parentheses, you can imagine all the different ways you can fuck this up. You can end up interpreting something that should be multiplication as subtraction. Like if I didn't write this set of parentheses, this might look like e to the x minus cos x, which it isn't. It's e to the x times the negative of cos x. And then in the second group, I've got a negative cos x, I've got a minus from the IBP formula, and I've got a minus out here from the previous IBP formula. So all these negatives need to be dealt with very carefully. Just follow your order of operations. Trust the algebra that you've spent the last few years learning. This is e to the x sine x. I'm not even going to bother with the big negative out front yet. I'm just going to come in here and clean this shit up. Negative e to the x cos x. That's the right way to write e to the x times negative cos x. And then here, minus minus will make a plus integral. I'll write the e to the x first because it looks better, times cos x dx. Now I'm going to distribute this negative. It's very important that this negative goes here and also here. So you'll have e to the x sine x plus e to the x cos x minus integral e to the x cos x dx. And now we stop for a minute. We stop and we stare at this until our brains flicker a little. Why should our brains flicker a little when we look at this?
Because you're just setting up an infinite loop.
Better than that. It's true. I could continue this procedure ad infinitum. Why? What's loopy about it?
E to the x never changes, and cosine just kind of flip-flops from two binary states.
Yeah, right, exactly. Every time I run an IBP, e to the x stays e to the x, and this guy flips back and forth between sine and cosine modulo a multiple of -1. In particular, my original integral has shown up down here. This is the problem I started with. So let me take this line and condense it. I've got this thing is equal to this stuff. So what we have here is integral e to the x cos x dx equals e to the x sine x plus e to the x cos x minus the integral of e to the x cos x dx. This step kind of feels magical because the answer is about to fall out. It's just going to happen, and it's not going to be the result of a calculus process. It's going to be the result of an algebra process. I'm going to add this integral back over to the other side. I'm going to treat this integral as an algebraic object and add it to both sides. On the left-hand side, I'll have 2 times the integral of e to the x cos x dx. And on the right-hand side, I have e to the x sine x plus e to the x cos x. The integral is gone. I added it over. Divide by 2.
So for these type of problems, let me get this straight. We need to keep doing it until it eventually gets back to like the original chunk we started with. And then we need to use algebra to eliminate it and then divide it by 2.
Won't always be a 2, but the vast majority of what you said there is exactly correct. Looping integration by parts works this way. You run IBP some number of times, once, twice, 3 times, depends on the problem. You run IBP until your original integral shows back up, maybe with some constant out front. Then you add all of that stuff back over to the other side. Because it's your original integral, it will be a like term. So you'll be able to combine it with this. Then just divide over by the resulting constant. And we always slap on a c. Really, the right behavior is to add the plus c at this line, because at this line, you don't have any integrals on this side. You do have an integral on this side.
Can we not factor e to the x and get 1?
You can factor in e to the x, but you're not going to get 1. You'll get sine x plus cos x. Sine squared plus cos squared is 1, but sine x plus cos x is not 1.
Oh.
So if you want to, you can write this as e to the x over 2 times sine x plus cos x plus c. That's fine. All right. So this is one way to attack these problems.
What would happen if the integral on the right side was a positive and then you have to subtract?
Yeah, that would imply that you've gone down an unfortunate path. It's possible, so let's talk a little bit about the ways this shit can go wrong. I chose u to be e to the x in my first IBP and in my second IBP. If in my second IBP, I'd swapped these and done sine here and e to the x here, then my second IBP would exactly undo my first IBP. And what I would end up with is something like e to the x sine x minus e to the x sine x plus integral e to the x cos x. Then, yeah, if this is a plus, you would have to subtract it over. But this integral minus this integral is 0, or at best a constant. You'd end up with 0 equals 0. So that's a sign that something has gone wrong, namely that your second IBP, rather than taking you further, just undid your first. So the sign of the integral that you deal with at the end should always be negative. If it's not, that's a strong hint that you made an error somewhere. Did you follow that? Do we want to see this like thing going wrong? Do we want to see what that looks like?
No, I got it. I got it.
Okay, how about other folks? Does anybody want to see how that can go wrong like that? It's a common enough error that I don't mind spending class time.
But yeah, I mean, sure, if you want to show us,
You want to? Okay, yeah,
doesn't
let's
hurt.
do it. So
Yep.
let me come back to this line right here. Let me come back to this line. And instead of doing this IBP, I'm going to do something else. So let me see. Do I have something I can cover this with? Yeah. All right. So, here. We're not going to do that IBP. We arrive at this line and we're like, okay, shit's looking good. I know what I'm doing. I need to run integration by parts again. So I set up my second IBP, only this time I don't follow the LIPET rule. I fuck up and I say, okay, I'm going to do it like this. Why not? No one can stop me. du, the derivative of sine, well, that's cos x. V, the integral of e to the x is e to the x. So let's see what happens. If you guys are writing this down, please do it on a separate page. Please copy this, everything that's visible here, copy it and do it on a separate page so you don't confuse the correct solution with the incorrect one when you look back. So what would I get then? I would still have my e to the x sine x here, and then minus, open big paren, e to the x sine x times e to the x minus integral e to the x cos x dx. Close big paren. Now when I distribute my negative, I'll have e to the x sine x minus e to the x sine x plus integral e to the x cos x. So this would lead me to the statement integral e to the x cos x dx equals e to the x sine x minus e to the x sine x plus e to the x cos x dx. This is a true statement, it's just not useful. If I subtract this integral over,
Zero equals 0.
yeah, we get 0 equals 0, right? This integral minus itself is 0. And e to the x sine x minus e to the x sine x, this is 0. So you get 0 equals 0, which is a true statement, but it's not at all helpful. You can always massage a true statement into 0 equals 0. It's just not going to get you anything valuable. And this is a remarkably common mistake. You might be looking at this saying, I would never fuck that up. Clearly this piece is 0, so I would recognize immediately that something went wrong. But if I start throwing some numbers in here, instead of sine x, I call this sine of 2x, and instead of e to the x, I give you e to the negative 5x, then these coefficients are actually going to be different. They'll be different enough that you probably won't spot that this is 0 right away. And the coefficient here will be different. So you might not be able to see immediately that what you've done is eat your own tail. So yeah, don't do that. The key to avoiding that, every time you run IBP in one of these looping harmonic oscillator integrals, just stick with LIPET. Choose u to be the exponential and dv to be the trig. The truth is you could do it the other way. You could choose u to be the trig and dv to be the exponential. Either one will work fine as long as you're totally consistent, as long as whatever you do in the first, you do in the second. But the safe rule, the thing I've just been telling people the last few years is just follow LIPET. LIPET will save you here. It will keep you from making that mistake. And we use it almost everywhere else in IBP, so we might as well use it here too. All right, so this is our first looping integral. This is the gentlest of all the looping integrals. They get harder from here. In your homework, you have one that's like, e to the negative theta cos 3 theta. So I want to do something kind of like that, where the coefficients get a little bit more challenging. And I also want to show you the other sort of fundamental looping integral, which is the odd power of secant. I want to show you the odd power of secant first, because the odd powers of secant, they're beautiful. And these are like, right, you do fundamentals and then you build from there. So last call for questions, comments, anything we'd like to see relating to this first looping example. You can find links in the modules to videos where I've got folks working example problems like this. One of them from Patrick JMT, I think, is titled A Loopy Example. And that's a nice one to work through if you're having trouble in the homework. So let me show you how to integrate odd powers of secant. To talk about odd powers of secant, the first odd power of secant is secant itself. Who knows how to integrate secant?
Use integration by parts by setting u to secant.
So that'll be for secant cubed. But secant itself, we need to know how to integrate as a non-looping thing, because this is one of our like base integrals that we'll be doing the higher powers in terms of. So the first kind of prerequisite for this is secant itself. And secant it's a U-sub problem. You guys remember how to integrate tangent? You write it as sine over cosine and substitute for the bottom. This is kind of similar to that, only it involves a really bizarre first step. I'm not going to cold call you to show me how to do it, but can you guys show me with the react? How many of you solved the integral of secant in Calc 1? It's okay if you forget it. I'm not going to make you do anything. I just want to see how many people's Calc 1 class even touched this. It's supposed to be done, but not everybody's does. Okay, so a few people, definitely not a majority. Ethan, Tyler, Kyle, Daniel, Matthew, I got you guys. All right. I'm always curious. See what other professors are doing. Here's how this is done. You remember the multiply by 1 trick? Like to rationalize a denominator, you multiply by √2 over √2 or something like that. Well, here we use the multiply by 1 trick in a really weird form. We are going to multiply by secant x plus tangent x over secant x plus tangent x. I can do that. I can multiply by that quantity. That quantity is 1. Multiplying by 1 doesn't change anything. So no calculus being done yet, just algebra. Now the secant over here, this is the same as secant x over 1. So if I multiply these fractions, the secant is going to get distributed across this numerator. So this is going to hit here and here. The result being integral secant squared x plus secant x tangent x all over secant x plus tangent x dx. So I get this big ass fraction. The numerator is secant squared x plus secant x tangent x, and the denominator is secant x plus tangent x. Right, because I think of this as like secant x over 1, and I multiply the fraction straight across. I know this looks like it's getting worse, but I promise it's about to get much better. What's the derivative of secant?
Secant tangent.
And the derivative of tangent?
Secant squared.
Secant squared.
So what's the derivative of the bottom? It's the top. This is the derivative of this.
Is this an ln problem?
It is.
I swear.
Yeah, so this is, I'll rewrite it like this. So make it a little bit easier to see the substitution. Secant x plus tangent x. And then that numerator I'll write over here with dx. Secant squared x plus secant x tangent x dx. So if we sub for the bottom, we sub z equals secant x plus tangent x, then dz will be secant x tangent x plus secant squared x all times dx. And that order of addition in the middle, you can change that. This is the same as secant squared x plus secant x tangent x dx. So under this substitution, this becomes the integral of 1 over z dz. Right, 1 over z dz. And the integral of 1 over z dz is the natural log of the absolute value of z. So this is the natural log of absolute value of secant x plus tangent x plus c. That's the integral of secant. And this is prerequisite knowledge to discuss any odd powers of secant. I would tuck this one away. In the same way that people remember that the integral of tangent is negative natural log cosine, or the integral of tangent, some people just write it as natural log secant, both are kosher. This is one that people tend to just remember. I encourage you to just remember this. It's not worth the time to go through this whole substitution process every time you need the integral of secant, but here it is, right? So this is the integral of good old-fashioned secant. Now, if we want to do secant cubed, what we're going to do is we're going to use integration by parts and some trig identities to loop that integral and get its answer in terms of the integral of secant, which we have here. Such a process is sometimes called a reduction formula. Questions on the integral of secant before we move to secant cubed? So this, just to be clear, there was no IVP, there is no looping here. This is just a little U sub problem that we needed to have out of the way before we can jump into the IVP. Going once.
Yeah, in the very first line, where'd you get the secant x plus tan x over secant x plus tan x?
It's a great question. It's just something that I chose to try. Fuck it, why not? Basically, it's a gnarly trick, right? Nobody would ever think to do that. It's not like a logic thing. It's not something that you're going to say, like maybe if I try multiplying by secant plus tangent over secant plus tangent, something nice will happen. No, it's just a trick. It's an old-fashioned trick. It's something that people have discovered works and is a way to get this integral without nastier tricks. So it's not a trick you're going to use anywhere else. It's a trick we only use on this integral, and that's why I say it's worth just memorizing this integral. But it's 1, right? Secant plus tangent over secant plus tangent, that is 1. So I'm allowed to do it in the same way that I'm allowed to multiply by 5 over 5 or root 2 over root 2. And it just happens to take this from like a really hard to see answer to a much easier to see answer from here. So yeah, it's a nasty trick and it's totally unmotivated. And I don't have any good motivation for it besides knowing that it works. But I promise you there's very few things like that in this class. In fact, I think this is the only time I'm going to show you a trick with no motivation. Oh, other questions on this one? All right, let's get into the good stuff then. So the good stuff is odd powers of secant. So let's try secant cubed. This is an IBP problem, as are all the other odd powers of secant. Secant cubed, secant to the 5th, secant to the 7th. They all require integration by parts and use of trig identities. Why I saved this for a second. How you choose to set up the integration by parts here is up to you. LIPET won't help you here because everything is trig, right? There is no L, there is no I, there's no P, there's no E, it's all T's. But I know how to integrate secant squared. That's easy. And I know how to differentiate tangent, or sorry, secant. So secant cubed can be split up as secant x times secant squared x dx. And I choose this piece as u and this piece as dv. Again, no help from LIPET here. We just have to follow our nose. But secant squared's integral is easy, right? I know who differentiates to secant squared, that's tangent. So that's kind of how I pick the dv as the piece I know how to integrate well. So that means v is going to be tangent, and the derivative of secant du is secant x tangent x dx. So here's my little IBP table. And according to the integration by parts formula, the integral of u times dv should be u times v. So secant x tangent x minus the integral of v times du. So tangent x times secant x tangent x dx. I can combine the two tangents here. Everything is being multiplied. And I get secant x tangent x minus the integral of secant x times tan squared of x dx. And this is where trig identities become useful. I like using this problem as a late example here because next week we're doing all trig integrals, 7.2. So trig identities are going to be your very best friend for the next few weeks, not just in 7.2, but in 7.3 also. 7.3 is called trig sum. My goal, knowing a priori that this is supposed to be a looping integral, is to make the integral of secant cubed show up again. So somewhere in here, I want to make a secant cubed show up. So I have tan squared and secant. I know that tangent squared is related to secant squared through a Pythagorean identity. Who remembers the Pythagorean identity relating secant to tangent?
you make it 1 over sine and then sine squared x over cosine squared x.
That's true, but it's not a Pythagorean identity. That's called a reciprocal identity. So let me start with the first Pythagorean identity. That's sine squared x plus cos squared x equals 1. Everybody remembers this, right? Now divide every term by cos squared. And you get sine squared x over cos squared x plus cos squared x over cos squared x equals 1 over cos squared x. Now rewrite these using the exact identity you just mentioned, Daniel. Rewrite these using the reciprocal identities. Sine squared over cos squared, like you said, that is the same as tan squared. Cos squared over cos squared is 1. And 1 over cos squared is secant squared. So this is what's called the second Pythagorean identity. This up here is called the first. First Pythagorean identity is item 1. Second Pythagorean identity is item 2. Rearrange item 2 to isolate tan squared. And you get tan squared x is equal to secant squared x minus 1. This is what we will use here. I will replace this tan squared x by secant squared x minus 1. And that will bring back a secant cubed. Now, being good mathematicians, we rewrite the whole line. Even though our hands are getting sore, we don't get sloppy on this shit. I'm replacing tan squared by a difference of 2 terms, so I need to include a parentheses. Integral secant times secant squared x minus 1 dx. The whole line rewritten. We're almost there. I'm going to distribute this secant over these parens, giving me secant x tangent x minus the integral of secant cubed x minus secant x. And you remember from the beginning of the semester, I said if you have in your integral more than one piece, like separated by addition or subtraction, you need to put it in parentheses. We're about to see a very good reason for that, namely this negative sign. Is everybody with me so far? Take your time, clean up your notes. I just noticed, Matthew, yeah, thank you. That was indeed the correct second Pythagorean identity. I got carried away and didn't see your correct answer there. Thank you for that. All right. So next, I have to split up this integral and distribute this negative sign. So I'll have minus integral secant cubed x dx plus integral secant x dx. This plus coming from this negative and this negative. Right, this negative here slaps both of those, making the second one positive. And now the magic thing has happened. My original integral has shown up. I have an integral secant cubed, and better, it's got the negative sign, which is what I need to add it back over, right? this piece, I know. This piece is the natural log. So let me add this back over. We'll have our similar line. So integral of secant cubed x dx is equal to secant x tangent x minus the integral of secant cubed x dx plus the integral of secant x dx. I add this piece back over. So my left-hand side becomes 2 integral secant cubed x dx. And my right-hand side is secant x tangent x plus the integral of secant x. The integral of secant x we did on the previous page. That was the natural log of secant x plus tangent x. At this stage, I should start writing my plus c's because there are no more integrals on the right-hand side. And our final step here is to divide by the 2. So it follows from this that the integral of secant cubed x is equal to all this shit divided by 2. Now c divided by 2 is still c. It's an arbitrary constant. Dividing it by 2 doesn't change that. Some people write this as 1/2 secant x tangent x plus the natural log of the absolute value of secant x plus tangent x. Some people would write it as all that over 2, and then you've got your plus c. And that's the job done. So I'll zoom out a little bit. You got all the good stuff in here. Here's everything after the IVP. Notice we only ran IVP once here. It was just one run of IVP and then clever use of trig identities.
Where you have secant cubed minus secant, why can't you just combine those and then you know the integral of that?
Well, they're not like terms. Just like x cubed minus x can't be combined into a single term, secant cubed minus secant can't be combined into a single term. You could factor out a secant, and that would just take us back to this line. But there's no simplifying this. And getting the secant cube to show up was my goal. Remember, I wanted to make this loop. I wanted to get this guy so that I could add him back over because my left-hand side is the integral of secant cubed. So getting this to show up was a goal of mine. We wanted that to happen. So this step is an intermediary on the way there. This is a good thing. But also, I can't really combine those. There isn't any way I can put them together because like x and x cubed are not like terms, secant x and secant cubed x are not like terms. So it's in other words, kind of an order of operations thing. The power takes precedence over the subtraction. Does that answer the question?
Yeah, I just had a brain fart. I was thinking you combine them, but you can't, so.
No, you're good, you're good. What else are we thinking? I know this is like a little bit overwhelming the first time you see it, so I want to give you guys a moment to process.
So right at the beginning, you had secant x times secant squared x. Say like the original question was like secant, I don't know, to like the 5th power. would it still be secant x times secant like to the 4th power? That way you can have just like one secant, or?
Well, I peel off the secant squared to choose as dv because I
Right.
know how to integrate that. So if I was given secant to the 5, I would split that as secant cubed times secant squared. And then
Okay.
dv would be secant squared, u would be secant cubed, and we would need the chain rule to cook up the derivative du. The truth is those get real gnarly. While it's true that all the odd powers of secant are dealt with in this way, the fastest way to integrate secant to the 5th is a quick IBP in term, and then your dv to v step there would be the secant cubed. But it's gnarly. I won't likely ask you guys to integrate any higher power of secant than secant cubed, at least not any larger odd powers. But this procedure is an important one, and the secant cubed integral actually shows up in a lot of really natural places as a result of geometry. So it's an important integral, this specific one. But if it were secant to the 5, you just have to play around. And the choice of u and dv that I would recommend guiding your decisions there by choosing a dv that you know how to integrate. Other questions or comments here? Okay, let me see how we're doing for time. We're probably approaching our break. Where are we? 153.
We're way over, sir.
All right, so yeah, let's take a little 10-15 minute break, and we'll come back 154. We'll come back at 2:10 to do a few more problems. All right. I'll leave this zoomed out a little bit in case anybody wants to look more closely. That's not really legible, is it? Here, how about this? You can't really see it. All right, I'll leave it like this. I'll be back in about 15 minutes. Unfortunately, when it comes to broken devices, PC, probably not. No, I haven't tried it. It's like one of those, oh, nice thing about homemade food. You pick it, it should be. Oh, that shit is in the store, it's like pet food, whatever. Just the way they compensate for the taste and you'll be all right. Yeah, all right, I got you. Well, quinoa and the fish are gonna have some special, but I don't think so. The only thing I think it is going to be very mindful of sugar consumption. Okay, okay, triglycerides. No, don't call them. They will call us. I mean, they will, or they will text us, or they'll email us. If they want us in their house, they want us to let us know. They will start making those mistakes. Probably. You know, I gotta finish this up. If I don't hear from them by the close of this is today at 5 p.m., I will send them a text first thing tomorrow morning and ask them, hey, when are we going to find out? That's not okay. Yeah, all right. I just don't want to bug them, you know? Like, who do you think about? Yeah, that's true. I got a few minutes here before I need to resume class. I'll send them a text now. Yeah, I'll do that. Ooh, another PS5 drop. They did a Best Buy did a drop while I was teaching an hour ago. They sold out. No, it's crazy. GameStop did a limited drop. It's probably gone 10 minutes ago. PlayStation 5, $499, online only. Yeah, already up. GameStop did a drop. The disc edition, they did like a regular drop today. At 10 minutes ago, I got the alert and saw it. We'll get there. I love you, baby. I'll send them a message now. Yeah. All right, but I gotta start teaching. Where it is. Okay. All righty. Oh, Oscar says Walmart's dropping again at 3. Hey, one of my students got our back on this shit, baby. There's a Walmart drop today at 3. Oh man, I knew I should have asked you guys. All right, tell me everything you know about PS5 drops. There's a Discord called Stock Drops where they notify new drops. So I've got a bunch of Twitters that I'm following, but they only let me know after the fact, and it seems like I'm always late, even though this last one was 10 minutes ago. They're all sold out. So Alp from my Calc 2 class says there's a Discord server we need to be watching called Stock Drops, and Oscar from that same class says that there's a drop today at 3 for Walmart. Yeah, I think Site Supply. I think that's the Twitter that I've got set up here. Is it Site Supply? Oh no, PS5 restock alert, stock alerts, stock up. All right, let's try that. This is sweet. I appreciate you guys. Just out of curiosity, has anybody had success? Select the products. Yeah, 3070. Yeah, GPUs are hard these days too, right? All right. So we're gonna follow this. Nice. All right. Yeah, the scalpers are the worst. Actually, one of my old friends from college, I saw him over the holiday break, talked about, oof, yeah, I see, I was gonna hit a 3. Talked about how his bot has been snatching PS5s and he's been selling them on eBay and making lots of money. And I love this man. This is a good friend of mine from, 10, 15 years ago. And I could just feel my blood pressure rising as he told me about the money he was making doing this, because I was like, God damn it, I've been trying to buy one of these things for months. And it's precisely you guys who've been making it hard. Not you guys, but my friend Derek is doing that scalping and using bots to buy and then reselling on eBay. But this is the world. It is what it is. He's making his money, so happy for him, but it is frustrating from the consumer end. Lucky enough to get a my first release of a 3 series from the same server. They work well. Okay, yeah, let me this Discord. Just tab over here. All right. It is now the time for us to get back to talking about calculus. So I do appreciate your guys' assistance with the PS5 thing. That is nice. I've been trying to get one of those for my life for a few months now. All right. So there's really only one problem that I want to work in lab today, and that's the more general damped harmonic oscillator. And then maybe we can work 1 or 2 problems from the homework, whatever's been driving you guys nuts. And then I'll let you guys go. We don't have a dedicated lab activity today. It's just about problem solving. So let's get in with more damped harmonic oscillators. You guys know why they call them harmonic oscillators, right? The sine and cosine are harmonic oscillators. Because as was mentioned in the lecture, when you pluck a string, that vibration is sinusoidal. And the damped, of course, is the decay factor, the e to the negative x or whatever. So yeah, the classic one here, we did e to the x cos x. I'd like to do e to the negative x sine 2x dx. It's the same sort of vibe. We're going to run IBP twice until the integral loops, but we need to track our signs and our constants very carefully through this process. So you have one in your homework that looks an awful lot like this, and you can use this as a model. We know to jump in with IBP, and we know following our LIPET rule to choose u as e to the negative x, and that means dv is everything else, sine 2x dx. du, the derivative of e to the negative x is negative e to the negative x, and then dx. V, when you integrate sine 2x, you get negative cos 2x over 2. The dv to v step here is a tiny little u sub, and we should be getting good at doing those. I think we called them micro u subs in our last class. That's a cute little name. You would substitute like z equals 2x. So dz is 2 dx. So 1/2 dz is dx. That's where the 1/2 or the 2 downstairs here is coming from. And then the antiderivative of sine z is negative cos z. So we should be getting good at those little micro u subs. And then we apply the IBP formula. So u times v there's a negative here, I'll make that clear, minus the integral of v times du. So that's negative cos 2x over 2 times negative e to the negative x dx. And again, when you're multiplying these things, please put them in parens so that it's clear that, for example, this is not being subtracted, but that you're multiplying those two. Now within the integral, I've got a negative here and a negative here. So this product will be positive. And the 2 downstairs can come out front as a 1/2. It's a constant multiple. I'll also clean up the front here. This is negative e to the negative x over 2 times cosine of 2x. And then here, this minus, I'll just carry down, minus the integral, because inside this product will be positive. I'll bring out the 1/2, and then inside there will be cos 2x times e to the negative x dx. Normally I'd write the exponential out front to make it look prettier, but it's okay. Now I'm ready to run my second IBP because this integral is looking pretty similar to this integral. All right, it's back into that same form. So I'll run my second IBP. U again will be the the exponential e to the negative x, and dv will be everything else, which is cos 2x dx. So du will again be negative e to the negative x dx, and v this time will be sine 2x over 2. So there's my second integration by parts table. Now, very, very carefully expand this integral using this IBP formula, this IBP table. First, we copy down everything else, right? This equals, equals, equals. You want a chain of equals, right? You want to be able to say your original thing is equal to your answer. So just good notation practices. Yes, your hand will get tired. Yes, it'll get cramped, but it's worth it. Now, minus 1/2, that integral is about to be replaced by a difference of 2 terms. So I need to make sure I open up a big paren. And then this integral from this IBP table is equal to u times v. That's e to the negative x times sine 2x over 2 minus the integral of sine 2x over 2 times negative e to the negative x. And then we close that big paren. So here's our first IBP formula, and then here's our second IBP formula done within the first. I have a lot to clean up here, and we're going to be careful as we do it. First things first, I would probably pop this negative right here out, make this a plus, bring this 2 out, make that a 1/2. So we'll have negative e to the negative x over 2 times the cosine of 2x minus 1/2 big paren, oh, sorry, big paren e to the negative x over 2 times sine of 2x plus 1/2 integral sine 2x e to the negative x dx, close big paren. Right, so this negative popped out, made this a plus. This 2 downstairs popped out here as a 1/2. Now I'm going to distribute this 1/2 over all these terms and this negative. So we'll get negative e to the negative x over 2 cos 2x. Negative 1/2 times this quantity is negative e to the negative x over 4 times the sine of 2x. And then this and this will be minus 1/4 integral, I'll write the exponential first, e to the negative x sine of 2x dx. So that is us handling all of the signs carefully, using parentheses as appropriate. Parentheses are your friend, right? When in doubt, use them. If you're not sure if you need them, you probably do. If you're really not sure, send me an email, right? Take a picture of your work, message it to me, I'll get back to you quick. So what we have is that the integral of e to the negative x times the sine of 2x dx is equal to all of this. Negative e to the negative x over 2 times the cosine of 2x minus e to the negative x over 4 times the sine of 2x minus 1/4 integral e to the negative x sine of 2x dx. So I'm going to add this quantity to both sides. I will add 1/4 integral e to the negative x sine 2x dx to both sides. So we don't always have a 2 over here. This time, have something different. If I take one of these integrals and I add 1/4 of these integrals, that's 1 plus 1/4 is 5/4 of those integrals. And that's equal to this stuff. And at this stage, we would start writing our plus c, because there are no more integrals on the right-hand side. There's just an integral on the left. So the appropriate time to add the plus c is now. And then to finish things, I need to get rid of this constant. So I'll multiply both sides by its reciprocal. So I get integral e to the negative x sine of 2x dx is equal to, well, this is a 1/2. 1/2 times 4/5 is 2/5. So 2/5 e to the negative x cos 2x minus 4/5 times 1/4 is just 1/5. So 1/5 e to the negative x sine of 2x. And the plus c stays the same. You don't need to change the plus c. Okay, so that's the result here.
So the way I wrote it was I put I copied the right side of the equation straight to the bottom, but I put the 4/5 outside in the parentheses.
That's fine.
Is the C inside the parentheses or outside?
I would leave it outside. The trick here is to remember that that C is what's called an arbitrary constant, meaning we think of it as running over all the real numbers. So if you multiply by a fraction, or you add 2, or divide by 5, or whatever, it doesn't actually change what C is. It just represents an arbitrary constant. So I would leave the C out of any arithmetic operations. You can kind of just ignore those.
Got it.
Professor,
Mhm.
how did the e to the negative x over 2 in the beginning become positive from being a negative before you added
Oh.
the integral to both sides?
Good catch. It should not have done. Yeah, it should have stayed negative. Thank you. Nope, that's an error on my part. Good catch. Yeah, thank you. So everybody, please, you heard Lydia's comment. This term should indeed be negative. I left it off. So make this correction. Please make sure this term is negative. This term is negative. Other questions or comments on this?
Could you further simplify it so that since e to the negative x is just 1 over e to the x, couldn't you simplify it by moving the e down to the denominators?
Yeah, I think the nicest kind of I like to leave it upstairs. Honestly, e to the negative x is a nice and well understood function. I wouldn't be inclined to move it downstairs, but if you wanted to, you could. Definitely an e to the negative x, a 1/5, and a negative can come out. So if you wanted to write this kind of maximally nicely, it's probably going to look like this. And then if you wanted to, you could move this e to the negative x downstairs as e to the positive x. But it's a matter of taste. I think e to the negative x is a nice decaying exponential. I like to leave it as that. But if you wanted to bring it downstairs, I wouldn't call it wrong. I'd certainly call it right. It's more just a matter of taste. Other questions or comments on this one? Okay. So these looping integrals, they are fun. They are a great way to practice your IBP skills. There's one other, I was thinking about other sort of problems that would make good problems for us to play with in the lab. And this gives me an excuse to introduce something that you guys probably haven't seen before, which we will need a lot later in the semester and to practice with IBP. So one of the things I was thinking about, how many of you have heard of the factorial function?
That's the exclamation mark, correct?
Yeah, it is. It is. This is the exclamation mark. N factorial is defined to be the product of all positive integers less than or equal to n. That is, it's n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. Now this formula kind of only works if n is bigger than 3, right? It doesn't really make sense if n is like 1. But the way it works, 1 factorial is 1. 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. I'll partition the page here. 5 factorial is 5 times 4 times 3 times 2 times 1. Do one more. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. So these are factorials. And they're really useful in discrete math. If you're trying to count things. It turns out n factorial is the number of permutations of an n object set. So if you give me, if I've got n people and I want to know how many ways can I arrange them in a line where the order matters, the answer is n factorial. Bunch of other things like that. They're also used to build binomial coefficients. But the kind of interesting thing for us right now about this factorial function, and we will use this a lot later in the semester when we talk about sequences and series, is that this definition only works for positive integers, right? What the hell? It turns out 0 factorial is reasonably well defined as 1. I can give you an argument that defines 0 factorial as 1 without any trouble. But what the hell is -1 factorial or 1/2 factorial, or God forbid, pi factorial? The definition above really only makes sense for positive whole numbers, right? We say we're gonna take whatever number you give me and multiply it by the positive whole number below it, by the positive whole number below that, and carry on down. No, Alp, I promise you won't have to integrate the factorial function. Not yet. I am going to make you integrate the reciprocal of the factorial function. That's called an infinite series, and we will do that in about 4 weeks. But I'm going to spend weeks developing the machinery behind it before we get there. No, what I want to do is I want to answer this question. How the fuck could we possibly define this thing for other inputs, for inputs that are not positive whole numbers? And it turns out that the answer here is best given in terms of a certain kind of integral. The best way to answer this is in terms of what's called the gamma function, for which we use the Greek letter capital gamma function. Now the gamma function, as explored by Leonhard Euler, is given as an improper integral. Gamma of x is the integral from 0 to infinity of e to the negative t times t to the x minus 1 dt. And this looks kind of scary, but if you think about a related function, so understanding this requires comfort with integrals of the form integral e to the negative t, t to the n dt. Really, gamma of x is x minus 1 factorial. That's how it works out. And in order to, the fact that the top here is an infinity, that's a problem. We don't know how to deal with that yet. I'll show you guys how to deal with that when we get to section 7.8. I just want to show you this thing now and then say, well, in order to work with that a lot, we need to know how to work with this. So I'd like to evaluate this for a few particular values of n. So an example problem here, and this is similar to ones that we've done in class. Let's evaluate the integral from 0 to r of e to the negative t times t dt, integral 0 to r e to the negative t times t squared dt. We'll do each of these, and then down the road, I'll show you a trick for evaluating a larger form with the aim to understand integral 0 to r e to the negative t, t to the n dt. And later what we'll do is we'll send r to infinity. So let's do the first one. Integral 0 to r e to the negative t times t dt. How do I do this integral? You can give me a starting point or a method or something we should do. Yeah, Matthew, IVP for sure. How should I choose u and how should I choose dv? Which piece is which?
E to the negative t is u, and then dv is t dt.
Hmm. So the exponential is way down here. I do have a polynomial here. The t piece is a polynomial. So really I want to pick u to be t and dv to be the exponential, e to the negative t dt. If we ran it the other way with t dt as dv, then the power of t would go up, which is going to make the problem harder. So my goal is to knock that power down. du will be dt and v will be negative e to the negative t. And what I'll see is that this integral is equal to u times v, which is going to be negative t e to the negative t, evaluated from 0 to r, minus the integral from 0 to r of v times du, which is just negative e to the negative t dt. Now, when we plug in 0 and r here, at the upper bound, I'll get negative r e to the negative r, and at the lower bound, I'll get 0. And this piece will become plus integral 0 to r e to the negative t dt. So this is negative r times e to the negative r plus, now here I find my antiderivative, that's just e to the negative t. And we evaluate him from 0 to r. At 0 here, I'll get 1. And at the upper bound, I'll get e to the negative r. And now I want you to imagine what would happen as I send r to infinity. What does e to the negative r do as r goes to infinity? Anybody remember these limits from 2.6 in Calc 1?
Plus 0.
It does, it goes to 0. And this piece would also go to 0. It's going to require some L'Hopital's rule. It's not as easy. So I just wanted to show you one of these runs. Oh, sorry, this should be a negative. So this is going to end up being a plus, and this will end up being a minus here. Sorry. In general, integrating higher powers, e to the negative t times t to the n, would require multiple applications of IVP. Rather than doing this and doing this, let me just show you how one run of IVP affects this guy. So just for fun. Your book also has some good problems along this line, but they're not problems that work well in WebAssign. So they're not problems that I want to give you in the homework, but I think they're fun to play with. So let's look at just one run. I'll do it as an indefinite integral, e to the negative t, t to the n, dt. I would run IBP, choosing u as the polynomial piece, which is t to the n, and dv as everything else, which is e to the negative t dt. Du would be n t to the n minus 1 dt, and v would be negative e to the negative t dt. So I would get u times v, which is t to the n times negative e to the negative t minus the integral of v times, oh, no dt here, sorry, v times du, which is negative e to the negative t times n t to the n minus 1 dt. So something kind of neat happens here. We'll have a negative t to the n e to the negative t, and then the two minus signs here will make a plus. The n can come out because he is a constant, and what's left is e to the negative t times t to the n minus 1. And this is getting at what I called a minute ago a reduction formula. If I call this thing, let's give this thing a name. Let's call integral e to the negative t, t to the n dt. Let's call that f of n. The t's go away, right? When you integrate this, there are no t's in the answer, but there are n's. Then what we've shown is that f of n, that original integral, is equal to negative t to the n e to the negative t plus n times f of n minus 1. I should have a dt here, right? This guy is this guy, just with n swapped for n minus 1. And if we were to evaluate this piece from 0 to infinity, it would go away in the same way several applications of L'Hopital's rule. So you end up with what's called a functional equation relating the original problem to the problem with one number smaller for n. Your book has a handful of things like this that I would like to point you to if you want extra practice with integration by parts, and also if you want to see why IBP is so valuable. So let's come here. There's only so much good stuff we can do at this point because we don't know how to handle improper integrals, but there are nevertheless some cool things. So if you look down here, there's a Wallace formula for pi. That's this thing. So problems 47, 48, 49, and 50 all kind of tie together. And if you work on these in the same way that I kind of just showed you for those, you'll arrive at a really neat formula. They call these reduction formulas because they take an integral of a power and it spits out some shit plus a very similar integral but with a smaller power. And then this result that you're able to get over here, that if you integrate sine raised to an even power from 0 to pi over 2, you get this really neat shaped product with pi over 2 at the end. And this is a fun way to compute pi, is through doing things like this. 51 through 54 are also really good problems if you want to practice getting powerful with IBP. But that's all I wanted to beat you guys down with. Not literally, but those are the things that I wanted to show you and make sure I showed you, and open up for you to ask whatever you would like to do. So is there anything that you would like to look at either from the book or from the homework before I let you go for this lab period?
Number 11 on the homework. I know about the rules for what to choose as u and dv, but there's two polynomials there.
Oh, then I probably wouldn't use integration by parts. I would probably just distribute, but let me take a look. Always go through this.
Well, there's a two polynomials and a trig function.
All right, which problem number was it?
Number 11, and correction, it's an exponential function that it has an addition.
Oh, okay, okay, yeah. So if it's all right with you, I'm going to ignore the 19. I'm just going to look at x e to the 2x over 1 plus 2x quantity squared dx. All right. Yeah, it's interesting. It's not entirely obvious to me even what we should do. But let's look at our Lipet rule. It's true that this piece up here is polynomial. But maybe the thing to do here is to peel off the exponential. So I can write it like this. And I'm thinking maybe I pick this for dv, and maybe I pick this for u, or maybe I pick this for u and pick this for dv. I'm trying to see if there's any.
Doesn't it make a difference which one you pick though?
It should, yeah. I think it will make a difference. I'm just trying to see if there's any obvious choice here one way or another, and I don't see one. I think if I differentiate this, it's certainly not going to get nicer, right? It's going to get gnarlier. We can look at those. So maybe this is a good problem to explore these two things. So choosing u and dv here is hard. I can think of a handful of ways to try and clean this up. Like maybe first we make a little u sub for 1 plus 2x. That would end up rewriting this a little differently and this a little differently. It might make things easier to see. But just for fun, let's look at both the derivative and antiderivative of x over 1 plus 2x all squared. The forward derivative here, we can calculate using the quotient rule. That's low d high, so that's 1 plus 2x quantity squared times 1 minus high d low, that's x times the derivative of the bottom here is 2 times 1 plus 2x all over the bottom squared. And this isn't looking especially nice, but you never know. Let's distribute things and see how it works out.
Can you pause for just a sec, just because that takes a little bit longer for us to figure out?
Sure. Yeah, here, I'll hold here for a second. All right, I'm going to pick up here. So now if we FOIL this out, I would get 4x squared plus 4x plus 1. And then when I distribute this, I'll have minus 4x squared minus 2x. And all of this is over 1 plus 2x to the 4. So the 4x squareds will go. And here 4x minus 2x is 2x plus 1 over the bottom is 1 plus 2x to the 4. And 2x plus 1 is the same as 1 plus 2x. So I can cancel those. The top is 1 plus 2x to the 1. So this would be 1 over 1 plus 2x all cubed. So the derivative of this thing is not too bad, actually. The antiderivative of x over 1 plus 2x squared. So it would require a little substitution. Z equals 1 plus 2x. dz would be 2 dx. So this is going to be, this is not pretty either. I'd have a z squared downstairs. I'd have a 1/2 dz. And then my numerator x, that's going to be 1/2 z minus 1, or z minus 1 over 2. So this is also quite a mess. I'd say this is 1/4 integral z minus 1 over z squared dz, which is 1/4 integral 1 over z minus 1 over z squared dz. Here we're going to get some natural logs. 1/4 natural log of z plus z to the negative 2 integrates to negative z to the negative 1. So that would look like this. We have a plus c here technically. But it's not pretty. Neither of these are especially pretty. So how do we want to look at this? I'm inclined to say the derivative of that piece is nicer than the antiderivative of that piece, especially if there's a chance that I would have to then integrate this. That's not going to be pretty. So I think probably picking this to be u and picking this to be dv is the way to go. Because if you choose this to be u, the derivative of that thing is actually not bad. So let's try that. Don't fret about the integral down here. If you didn't get that copied down, you don't need it for this. I'm going to say we'll run IBP with u equal to this rational function, x over 1 plus 2x squared, and dv equal to e to the 2x dx. Then du, we calculated the derivative here as 1 over 1 plus 2x cubed dx. And v here, the antiderivative of e to the 2x is 1/2 e to the 2x. So this is what I would try at first. And then following my IBP formula, we'll see if we get something better or worse. So I'll have u times v. That's a little scary looking. That's okay though, because it's out of the integral. I don't need to worry about it. Minus the integral of v times du. Times 1 over 1 plus 2x cubed dx. From here, what I'm thinking is probably a substitution. In this integral, I'd like to substitute for 1 plus 2x. And we might try that at the very start. It might make life a little easier. But let me just write this down. I'll clean this piece up. This is x e to the 2x over 2 times 1 plus 2x squared minus 1/2 integral e to the 2x times 1 over 1 plus 2x cubed dx. So in the resulting integral here, I would consider substituting for the quantity here, 1 plus 2x. And then in this integral, we'll make the sub z equals 1 plus 2x. dz is 2 dx. We're also going to need the fact that z minus 1 is equal to 2x. So this will become e to the z minus 1. What are we going to have? 2 dx. We're going to get another 1/2 out. I'll have e to the z minus 1 times 1 over z cubed times 1/2 dz. This is looking pretty bad, if I'm honest. I'm fairly certain that there is no closed form antiderivative for functions like this. E to the z over z, I know you're totally screwed. So e to the z over z cubed, I'm thinking is not going to be any better.
The way WebAssign recommended me do this question, and I found it really easy. The fractions actually ended up canceling out in the second integration, is to split it
We're going to need
top and bottom to have u equal to the bottom and then dv equal to the top of the original integration.
Yeah, so let's try that then. This isn't looking good. This is looking pretty bad. You said WebAssign recommended splitting u equals the top and dv.
U equals the bottom and then dv equals the top.
So the thing is, u times dv needs to be equal to the whole thing. So you mean like 1 over 1 plus 2x squared?
Yeah, sorry.
Okay, yeah, no, that'll work. Okay, so x e to the 2x dx. This is a kosher setup. du, we can calculate this using the chain rule if we want. That's 1 plus 2x to the negative 2. So the derivative there would be negative 2 times 1 plus 2x to the negative 3. So we'll have 1 plus 2x cubed. And then we'll get another factor of 2 from the chain rule. And v here, this, now we're having a little integration by parts to go from dv to v. So this is a bit of a tedious thing. I'm going to leave space there. We'll come off to the side somewhere and do the calculation. Where do I have extra space?
Sorry, I just double checked. You were right. They did do u as the top and
That's
dv
okay. No,
as
no.
as the fraction. I'm so sorry.
No, don't feel sorry. Don't feel sorry. This is a tricky problem. So we're going to set u to be x e to the 2x.
Yes.
And then dv as 1 over 1 plus 2x squared dx.
Yes.
Okay, this should be somewhat manageable. We won't need IVP to go from dv to v. That's nice. Here we will need the product and chain rules. So this will be 1 times e to the 2x plus x times 2 e to the 2x dx. And v here would be the integral of this. We can come off to the side. 1 over 1 plus 2x squared dx. You do this with a little u sub. And you would get 1/2 integral z to the negative 2 dz, which is 1/2 negative 1 over z. Yeah. Negative z, I'll write it like this, to the negative 1. So that's going to be negative 1 over 2 times z, which is 1 plus 2x. All right, let's see what we get here. So here's my IVP table, and each of those steps was a little bit complicated. Going from U to DU required a product and chain rule. Going from DV to V required a little U substitution, a not totally trivial U substitution. But according to all of this, my integral should be equal to U times V. So that's x e to the 2x times negative 1 over 2 times 1 plus 2x minus the integral of v times du. Oh, and I see, if you simplify du here, if you factor out e to the 2x, you get 1 plus 2x dx. This is very clever. I've actually never seen this before. And I've been doing this for years, so this is cool. So v times du, this is a new problem in this gen of the book. This is very neat. And then du is e to the 2x times 1 plus 2x dx. Very cool. The miracle here is that the derivative of x e to the 2x contains a factor of 1 plus 2x. And that's the only way to get rid of this 1 plus 2x from the bottom. So if we rearrange, clean up and rearrange, I have negative x e to the 2x over 2 times 1 plus 2x. The minuses here will make plus integral. I'll write the exponential out front, e to the 2x. And then here I have 1 over 2 times 1 plus 2x times 1 plus 2x dx. And that is really nice because the 1 plus 2x's cancel. Pop out this 1/2. And what's left in here is just e to the 2x dx. That is so nice. And now one more little u sub in here. We really don't even need to write these down at this point. This is negative x e to the 2x over 2 times 1 plus 2x plus. There's a 1/2 here. And when I integrate e to the 2x, I'll get 1/2 e to the 2x. So this will be 1/4 e to the 2x plus a constant. Very cool. Yeah, I don't know how long it would have taken me to see this, honestly. I think I probably would have tried a few other things before trying this. So big ups to anybody who saw this quickly. The magic here being that if you differentiate this using the product rule, you will get a factor of 1 plus 2x. After you pull out the common factor of e to the 2x, there will be a 1 plus 2x that can cancel with the 1 plus 2x that will be left downstairs in v. It's very, very nice. It's super slick. Let me pull the camera back so we can get the whole thing in the view. We don't end up using this way of thinking about it. This was not necessary. So straight from here, we choose this for u and this for dv. And that works. Very, very nice. Is there any way we can incorporate that into our LIPET rule? I don't think so. I think this lives well outside of LIPET. It's just a good problem. Comments or questions on this?
I think the only question is, when is the next office hour?
Next office hour is going to be tomorrow at 1 p.m.
Okay, I'll put it on my schedule. Yeah, my mind is just melted from all this.
These are
I'm trying. I'm trying my best, but you know, once calculus starts getting into moon runes type stuff, it sort of burns me out.
I can understand that. If you're feeling overwhelmed by the challenging problems, come back and practice a few of these early problems from section 7.1. These will help you get your bearings. So this fellow is number 21. I think any of these earlier ones, this one is a looping integral. He's a little bit hard, but anything up through number 16, I think should be considerably more tractable. I would pay careful attention, especially to problems like 5, 7, 9, 10, 12, 15, and 16. Those would all be really good kind of warm-up problems. And I think most of those are in your homework. But any other thing here? Or of course the examples, there's lots of examples in here that you can work through. Any other parting questions? Comments? All right, then I'll go ahead and let you guys go. Please continue working hard on this homework. Remember, it really is like building up any new skill, learning how to hula hoop or skateboard. It's going to take some real time. And it's not always obvious. Oftentimes it's not obvious. And you need to try a few things like we did here. So I encourage you guys to play with things, have fun working on them. Don't feel sad if it doesn't come out right away. Just try something else. And then when the victory comes, it'll feel great. If you do get stuck, come by office hours, next office hour tomorrow at 1 p.m. or shoot a picture of your work to me. Yeah, I'll check the PS5 drop. Thank you, Oscar. Take care, guys.
Great day, Professor.
Oh yeah, question?
Yeah, if we want a homework extension, do you want us to, like, I know how we can write a description why we need the extension. Do you want us to like do it there or email inbox?
Honestly, it doesn't matter much to me why you need the extension. You can just leave that part blank. I'll always grant it for 1 week.
All right.
Yeah, unless
Thank
there's
you.
something in particular you want to share with me. In that case, feel free to write it in the extension thing.
Okay.
Have a great day,
But
Professor.
in WebAssign, not through email or inbox?
WebAssign preferred. If it's related to the extension request, go ahead and include it in the extension request.
All right, sounds good.
Anything else you want?
Thank you.
All right, take care, guys. Have a good afternoon.